My name is Manya Agarwal, and I want to present my report that I prepared for assignment of CML 7 to 9. Let's start with the first question, which says identify the point group of the crystals that were given to you by analyzing the morphology. Explain them with the help of figures and photographs of the crystal. So, the crystal that was given to us is shown in the bottom right. So, this image that you can see is of the crystal that was given to us. So, what is morphology of the crystal? It is the external appearance. Like when we allow the crystals to grow for a longer time, the shape, the external, how they look is what determines, is what is called as the morphology. Somehow the internal arrangement is reflected in the external morphology, and we are asked to find the geometry and the point group of the morphology of our crystal. So first of all, I identified the symmetry elements present in the crystal, and I found that it has a twofold axis of rotation, along with two perpendicular mirror planes that are parallel to the axis of rotation are present. So this is shown in this upper image, the three symmetry elements. So these symmetry elements are characteristic of the orthorhombic crystal system, and they should correspond to the MM2 point group. Also, I confirmed my thinking here uh, by finding this image, by finding that orthorhombic crystals of barite also crystallizes, also resemble the same morphology of the crystal. So these are shown in the bottom left. So this after this, I confirmed that my given crystal is also orthorhombic, and the point group is MM2. Next, the question 2 says solve and refine the crystal structure using OLEX2 software for the three datasets provided. So we were provided with three datasets for three different molecules. The first one being HCT, the second one is the ROPA, RUPA, and the third one is RMAL. So the data files consisted of .ins and .htl files. The .ins files has the lattice cell parameters and the space group information, and the .htl file contains the HKL reflection and the corresponding intensities and the error. So using that information, um, we will use the direct method for the structure prediction using the OLEX2 software. So I gave these two files to the OLEX software, and then it generated this electron density map. So basically, the electron densities are shown with these, are represented by these spherical balls, as you can see in this image. So by giving these data for the first HCT molecule, I obtained this type of electron density map. After this, we will be using direct method, in which I have assigned the spherical atoms with the atom that they could represent. So I identified the atoms that could be that could resemble the electron density by seeing these values shown on the right. The error tells you if you are working in the right direction or not. By a hit and trial method and many iterations, I reached at the crystal structure which is shown in the second image. Then I refined my crystal structure and I checked the R factor. The residual factor, the R factor was less than 5%, which means that my predicted crystal structure uh, is well aligned with the actual structure. And also I checked the maximum peak and minimum peak, which are less than 0.6. Um, So I refined this structure, and then I checked the R factor. And lastly, I obtained the .cif file by clicking on this ACTA. The .cif file contains all the relevant information of my crystal structure, of the crystal structure of HCT. So it contains the lattice cell parameters, it contains the space group information, and um, the crystal geometry, all that information that is needed is obtained from through this software. After that, I did the same thing for the other two data sets also, and I obtained the .zip files. Next, we are asked to make a crystal packing diagram using VESTA for each crystal structure we solve. So the .zip files that we obtained, we gave it into the VESTA software. The VESTA software is very nice, like it spontaneously generated the crystal structure, the crystal arrangement it showed, and for the HCT structure, which has this molecular formula, it crystallizes in a monoclinic unit cell. And along the three directions, that is the along A, along B, along C, if we see the crystal, these are the crystal arrangements. So we can see that in all the three directions, the packing is different. Some atoms are exposed, different atoms are exposed at different phases, and that is seen for this HCD. For the ROPA also, which also crystallizes in the monoclinic unit cell, I saw the lattice, the crystal arrangement in the three directions. Similarly, for the RMAL, it also crystallizes in a monoclinic unit cell, and these are the crystal arrangements in the three directions. The question 4 says us to simulate the powder XRD patterns for the structure we solved. So for obtaining the PXRD pattern, earlier only we used the .zip files in the VESTA software. So .zip files, the PXRD pattern can be calculated. The peak positions are calculated by the unit cell parameters that are found in the .zip files. So the peak positions we can get from there, and the corresponding intensities can be found by summing the structure factor for all the structure factor for all the planes. For a given plane, the structure factor can also be calculated, and the intensity is nothing but the structure factor is rated to the square of structure factor, and the software does it through itself. The internally it calculates the PXRD pattern, and the simulated PXRD pattern for HCT looks like this. So the PXRD pattern, it is a plot of intensity versus the 2 theta, and we can see the reflections. So the HKL reflections and the intensities can be seen from here. For the ROPA structure also, I got the simulated PXRD pattern. And for the RML also, I got the simulated PXRD pattern. So this is a very nice way to, it minimizes, it is a very nice way to get the simulated PXRD pattern, and it minimizes many errors. Like if you calculate it is very ideal case like the simulated one, but in the real PXRD instrument, we collect the data and we find that the peaks are broadened because which can be due to many reasons, also the thermal factors and the strain, also the preferential orientation. So all those factors contribute to the peak broadening, and also the intensities may vary, but the absolute intensities remain, but the relative intensities remain the same. So that was all for this assignment, and I want to mention that I really enjoyed doing this assignment, especially that OLEX 2 part where we had to choose the atoms to the electron densities. It was quite interesting. And yes, I learned a lot through not only through this assignment, but yeah, through the course as well. Malak, uh, through the course, which was summed up in this assignment. So this was a good experience. Thank you.